Right, I'm not 100% sure how this thing works, but no. I'll put just a guarantee there. Okay, so I'm going to be talking about the Multi-Brain Toolbox, which has been in SPM for a little while now, but I haven't done a talk about it, so it was time. Plus, what I originally proposed wasn't quite working as planned. So, anyway, before I go on about the Multi-Brain Toolbox, I'll just put it into context and compared to the unified segmentation method, which many people are using. So most are probably familiar with the unified segmentation. So I'll start with, I'll start simple, Gaussian model. This is how we represent it. We've got our data F, which could be an image of kind of Gaussian random noise, or it could be multi-channel image with random noise with a particular covariance matrix. And I indicates the number of voxels. Right, so that's starting simple, but with real images, it's not random noise. So we use Gaussian mixture models. So Gaussian mixture models are a way of encoding probability density functions. So that's actually a joint histogram fit with a Gaussian mixture model, and that's the Gaussian mixture model representation of the joint intensity histogram. And the Gaussian mixture model involves kind of changing the basic Gaussian. So we've got this, we have K Gaussians, we have some mixing proportions, and we add a positive linear combination of Gaussian distributions together to get our representation of the probability density. We have these latent variables, which are basically you take priors, which is mixing proportions, and you've got a likelihood. You add the log prior and the log likelihood, run it through a softmax, and it gives you a belonging probability or a responsibility. Although, in there, that's supposed to be kind of categorical. So you've got an indicator variable indicating which Gaussian each voxel will be drawn from. So we need to modify the Gaussian mixture model to include intensity non-uniformity correction. So here we have an image before correction, after correction. We need that in order to get kind of meaningful intensity distributions that will separate, say, gray and white matter. So that's the gray matter and white matter intensity distributions after correction, before correction. And without the correction, there's a lot of overlap in the intensities. It works multi-channel. So if we have photon density weighted, T2 weighted, we can, is this working? Yeah, before and after correction, so that differences are very subtle. And it will change the joint intensity histograms and enable the better separation of voxels according to their intensities. And here's another example. So original image, the corrected image, and we've got a bias field or an intensity non-uniformity field, which is the exponential of a linear combination of smooth spatial basis functions. So this is bias correction, another part of the model. Yeah, that's basically it. And then the model has deformable tissue priors. So if it can, so rather than using mixing proportions to give priors for the different tissue types, we can have deformable tissue priors that get overlaid on the image that we're segmenting. So that would be kind of a segmented image, and those will be the tissue priors deformed onto the image. So we've got kind of registration component in the model. We parameterize our deformations as displacements. Well, in the old unified segmentation, we parameterize them as displacements in X, Y, and Z, which gives us this deformed mesh that we can overlay on the tissue prior. And if you straighten up the mesh, then we get a deformed version of the tissue priors that get overlaid. Then there's some other parameters to kind of tweak the relative scalings of the priors. So deformable tissue priors. Tissue priors. We have some representation of a deformation, which is regularized. But we talk about some notation here. So the circles kind of indicate things that are gray circle is split data. So the latent variables are kind of treated as random, whereas other things are treated as point estimates that we make. So yeah, tissue priors. That's basically summarizing image registration, which is quite a complicated field. Right, so what happened in multi-brain? We've got a couple of papers out of it, but they're just conference papers. So I'll start by a bit about learning tissue priors from populations of subjects. So we take our basic model and we do it over multiple subjects. And we have these parameters that we learn from the data. I think that's the only difference, really. So yeah, we'll make point estimates of tissue probability maps. And these are a kind of logic representation of the tissue priors. So rather than producing tissue probability maps, we produce something more akin to log tissue probability maps. So the actual way that the tissue maps are represented is like that. But if we run it through softmax, we get the actual tissue priors. So yeah, with the tweaks that were included, we can get better image registration according to overlap, which not everyone thinks is a good idea. So with the LPBA40 data set, it was basically using hand annotated MRI, aligning the MRI scans, and then assessing how well the hand annotations overlapped. Compared against various, or Mikhail compared against various methods. So that's the best method from the multi-brain. Sorry, the best result from our multi-brain. The best result from voxel-morph, which is one of the competitors. The worst multi-brain results and the worst voxel-morph results. And we compared it against some of the results from Klein's 2012 paper, where he compared lots of methods. So the green circles are multi-brain. One is using the pre-learned template. That's this one, I think. Whereas the solid green is doing a template as it goes along, constructing a template. And this is just looking at the overlaps in various brain structures against supposedly better methods, such as SIM or ADS, and shoot, so on. And these green circles are all to the right, so we've got better overlaps against these supposedly well-performing methods. Did it on ISBR 18. And yeah, this is where the kind of more precise delineation of the structures, and it makes it easier to get overlaps just by decreasing the amount of regularization. So again, we have the multi-brain method. All the spots to the right are these so-called better methods that are in fMRI prep and so on. Yeah, so that was the registration and the changes to the deformable registration stuff. There's another modification in multi-brain is to include priors on the intensity distributions of the different tissue types. So now we're treating these covariance, well, precision matrices and means as like random variables, and we put priors on them. But we maximize the likelihood of the priors so that they're not really priors. There's an option to use uninformative priors, or you get to learn the priors from population subjects. So that's just a representation of priors like that. But with the priors, it also allows us, or we can use these priors to kind of help with missing data, because real MRI data, if you've got multiple scans of a subject, you might have different fields of view in the different scans. And if you want to use all the data together, you need to be able to handle missing data. So an example from the exit data set, we've got reasonable coverage from the T1 rated, but less coverage from the T2 weighted. So that is an attempt to indicate what the missing data looks like. So we have points where we have known voxels or known intensities for both modalities, but we have lines if we only know the intensities of one image. And we need to make use of the, well, we need to kind of fill in the missing data in a kind of iterative EM type way to make the best use of the data. So with images, the fact that we can handle the missing data allows us to do cross-validation. We can see if we've got a good model by how we can assess how good our model is by how well it can predict one modality from another modality. Yeah, so a bit more. So we have our template data, which is a load of tissue maps. So the different colors indicate the different tissues. We can overlay that on the image that we're working with nonlinear registration. And then each tissue type will have a different multivariate Gaussian associated with it. And use these multivariate Gaussians to kind of. So if we have say a value around 400 of proton density weighted, and the tissue prior set belongs to this Gaussian, then we know we should have a value around here for the T2 weighted in this example. So yeah, it was tested. Michael tested it with some data where bits were chopped out. So we fit the model to proton density weighted, T1 weighted with bits chopped off the sides of the brain, bits chopped up front and back into T2 weighted. And then just use the model to infer missing data. So this is the inferred T1 weighted. It didn't do a terrible job. Missing data, building data, missing data. Oh no, sorry, 21. Oh yeah, these are inferred. So that data was imputed. That's the ground truth. More examples, and then we can see how Yeah, so if we've got a completely missing channel, then we can just use the tissue priors to say what the covariance matrices are to help kind of impute the missing data. And it was also done with MRI and CT. We didn't train it to produce tissue maps that are appropriate for CT. We used kind of tissue maps derived from MRI images, but let it learn the normal Wishart priors for imputing the values of the missing data. And used T1 weighted, T2 weighted to try and infer CT data. And it didn't do too badly with proper training data. They would probably do a slightly better job. So it handles missing data. It learns normal Wishart priors for the data. It's got labels, and the way you in addition to feeding images, you can feed labels, but the way it handles labels isn't ideal yet. So the mixture model was extended to be a mixture of Gaussians, but also a mixture of categoricals for the labels. So I won't dwell on that too much, but some of the applications. So based on this framework, Mikhail built his CT Seg toolbox, which has been used by a few people to do voxel-based morphometry from CT data, including, the last one is by Dr. Strange, now Professor Strange, this group. It's been used by, or basic ideas have been used by Patrick's group in Zurich, because the MRI atlas doesn't cover much of the neck. So if you want to do VPM on brain and spinal cord together, or statistical analysis of brain and spinal cord together. And yeah, we've also, okay, I should say rejected. But it works well for giving. So that paper was about using deep learning, but feeding in log priors and then getting a deep learning model to learn log likelihoods. And then you can add the log priors and log likelihoods and then run them through softmax to get much better segmentations, like 200% improvement in dice. Whereas normally, if you've got a deep learning paper and you improve dice by 0.3%, you get a publication. Other applications. So some people wanted to generate atlases from other species. So there's a kind of population atlas of macaque brains. And yeah, many of the ideas have been used by Clara, my finishing PhD student, who uses a kind of simplified version of the model to jointly cluster quantitative MRI and diffusion data, where the diffusion data is a result of probabilistic tractography from the FSL crowd. So we've got the multinomial probabilistic tractography, and we've got the QMRI. So we've got the mixture of categoricals, roughly, and mixture of Gaussians, clustering things together. So people that contributed to these extensions are here. This guy you might recognize, It's funded through various different sources. Thank you.